Hi, this is Mrs. Lemke, and today we are not really learning new content per se. It's more like we're just looking at integrals in different ways and considering different things that happen when we use integrals in application. So hopefully this helps you to understand why integrals are used across a lot of different fields. It's not so much that we're going to look at story problems today, but you'll just notice that your brain thinks differently in different contexts, even when math is kind of similar. And I think that's fascinating. That's why calculus gets used in physics and in economics and in all sorts of fields in addition to math. So I'm starting in your packet on the page that says integral as an area function. And in this way of thinking about integrals, what we are doing is we're considering the situation where we have a function that matches our integrand. So the picture here is of function f. F is our integrand. That's the word for something that's inside of an integral. And you'll notice that the function that it's set equal to is called g of x. So of importance here is when we look at this g of x, we should notice that the independent variable is one of the bounds. That's of interest to us. That's going to help us think through the questions that we're being asked. So since g is a function of x, we could think of x varying, right? That is what a variable is. It is something that varies. And so if you think about the fact that the lower bound is at 0, think of starting at 0, and then as x increases, x is the location of this purple line. So for instance, g of 2 would mean that I am here at 2, and I want to include all of the area under the curve that has filled in between the blue line and the purple line. The blue is my start because the lower bound is 0. And if I were looking at g of 2, like I'm going to right here, g of 2 would mean the area that has been swept through by that purple line moving. Whereas at the beginning, the first question I'm asked about here is g of 0. G of 0 would mean the purple line is where the blue line is right now. So that this purple line is over here, right? And so the space between the blue line and the purple line doesn't exist. They're both at 0. And that helps me to think about that first problem. So g of 0 is going to be a value of 0 because there is no space at all. Whereas g of 2 would be that space that I just indicated in red, and that would be the quarter circle. G of negative 2 would mean that I still start from my start of 0. That's part of this function. It's built in that the start is from 0, but the area that I would be sweeping through would be to the other side, and that is going to impact the signs of what I write. So I will write out here my thinking on this. So g of negative 2, if you just substitute negative 2 into that, if I plug negative 2 in for x on the left side, I have to plug in negative 2 for x on the right side of my equation. And since those bounds are backwards, I've got the smaller number at the top. I don't really like that. I use a property of integrals that lets me reverse the bounds. And now this part, not the negative sign, but that part just refers to this area, which again is just going to be pi, but I have a negative sign because of the bounds being in the wrong order at first. Okay, so there is my answer for the first 3. These, okay, you can think again about area. Here I am not looking at G, right? This is just asking about area. This is just asking about area. This graph is given to be function f. So in D, I'm just being asked to think about the area from 2 to 4. So that's this little bit. And that's going to be area of a triangle, but negative since it's below the x-axis, since the region is. So negative, and then 1/2 base times height, so -1. And then in the next problem, I'm going to observe that the only difference is that the bounds were reversed as compared to the previous question. So this has to come out to just be the opposite of -1 or 1. Now you might say, why can I have area under the curve be positive? Well, if I have a negative, right, I have negative because of bounds being reversed, and I have negative because of area being underneath, that's going to yield a positive answer because I have opposites in two different ways. All right, the next one is the area from 3 to 5 under the curve. So here's 3 and here's 5. And you can note that this blue region and this purple region are congruent, but they are opposite in sign because of the above and below axis issue. So this would have an area of 0. Okay, net area of 0, you might say. Now we're back to thinking about function g here. So recall function g was defined back here. And so we're going to have from 0 to 5 the integral of f. F is my picture up there. And so I'm going to look at the accumulation from 0 to 5. Taking my previous answers into account, that should end up with pi minus 1/2, all told. Some stuff cancels and so forth. And then this last one, if I have a different function, now called h, and I'm evaluating h at -2, then first thing I would personally do is reverse because those bounds are in the wrong order, which means I have an opposite sign at the beginning. And then I'm going to think about the different areas. Depending on how much you simplified, this is what you should have. Okay, so the next page that I asked you to look at is page 51. And this is what I personally call the poetic version of the fundamental theorem of calculus. That is a name that I made up, but you'll see why in just a little bit, I hope. Okay, so in problem 1, I'm just going to make use of fundamental theorem of calculus part 1 and know that if I anti-differentiate and I have a definite integral, I would take my antiderivative, I'm going to plug in the bounds, and I'm going to subtract. The antiderivative of f prime is regular f. And then I have bounds at 3 and 1. Remember that vertical line with the bounds just holds on to my bounds and shows that I already anti-differentiated. So this would be f of 3 minus f of 1. Okay? Now, if you kind of ignore that middle step for a quick sec, okay, and then just look at this statement as a whole, what I'd like you to do then is isolate f of 3 in that statement. So let's go ahead and do that. So what we did is just take this f of 1 term and add it over to the side with the integral. Okay, so I'm writing it in that particular order for reasons that you'll see in a second. Okay, but if you didn't write it in that order, no big. Okay, so now more generically, right, that those first two problems we were looking at a specific 1 and 3, just to not have only letters in the problem. But if we were to just think about this more generically, right, I would know that this would be the antiderivative with the bounds plugged in. That's from fundamental theorem part 1, as we number it. And if you take that statement and isolate the f of b, you'd have the function value at a plus the integral from a to b of f prime. Okay, so now I have an idea of how I could go about finding different points on a function if I know about the rate of change and I know a different point. So this is asking me to find f of 2. So think of that as my f of b. And I know f of 1. And I know f prime. So I'm going to take my f prime here. Instead of writing f prime, I'm going to actually write the equation. and my bounds are going to be 1 and 2. Now just notice I'm just following this format, right? This number matches that. This number matches that, right? I'm just following that as a format. Okay, now let's remember how to deal with this relative to use on the calculator. So I have my f prime equation slotted in here already. And we can look at a graph of that if we so choose. I don't know why I have my axes off center, but whatever. Okay, and then they would like me to determine the value of that integral from 1 to 2. So I can go in my math menu and actually, just kidding. I'm going to go to calculate and I'm going to go to item number 7. It's going to ask me some questions. So I want my lower limit, they call it, or lower bound, I would call it, to be 1. So I'm just typing a 1. And I want my upper limit, what I would call an upper bound, I would like that to be 2. So I'm just going to type a 2. My calculator will show me this nice visual and give me a value of negative 0.49. I'll round it to 5. Negative 0.495. Okay, so since my initial value was 3, I'm adding 3 to the value I got from my definite integral. Okay, so back on my paper, this part was 3, right? The f of 1 was 3, that was given. And then I want to add my calculator value, and my answer was that, 2.505, let's say. So that shows an application of the general idea that is as follows. If I have f prime and bounds a and x, I know anti-differentiating f prime is just going to give me the function f. I put in my bounds accordingly. And then you can see if I want to isolate for the f of x, make myself a new function. That's f of a plus, and then this integral from up above. Now let's explain why it's called poetic version, okay? And I actually think this might be easiest to see with number 4 up above, okay? So if I want to know where something is in the future, let's call B the future. I can take where I start from, okay? Let's call A the start. So I want to know something in the future. That's going to be where I start from, plus the accumulated changes. So accumulated or sum of changes would be this integral, and change is what a derivative is. So I add up all the changes in between. Where I am in the future, is where I start from plus the sum of all the changes since the start. Isn't that like what life is, friends? I'm just saying. I think that's what life is. That's why I call it the poetic version. It's meaningful. Think about you right now. Pretend you're age 17, okay? Where you are at age 17 is where you started at birth, plus the accumulation of all the changes over your life. Boom. Poet, that's poet. That's, I couldn't decide if I was saying poetic or poetry. That's poetry, baby. That is poetry. Okay? Let's look at page, I said page 50, but I think that's a lie. Okay, let's look at, where is this? Hold on. Okay, sorry about that. I just realized my page number mistake, and I also had somehow lost the graph out of that document. So that's back in the electronic version of your packet, but clearly you need to add this picture to your paper copy. Sorry about that. Okay, so let's work through this one. This says the graph of a differentiable function on the interval from 1 to 7 is shown, and it is true that f of 3 is 2.5. It is really important in this problem that we keep track of the fact that this is f. So when I'm being asked things about, say, h, I don't just look at that graph and think I'm looking at h. Okay, so it says in here that h is my accumulation of area starting at 1. Okay, so when I am asked to find h of 1, that just would mean I plug in 1 for that top bound, and since my bounds are identical, there's no space, and something that is doesn't have any space can't have any area. Okay, now in the next bit, I need to bear in mind that if I were taking the derivative of this function with my independent variable in the bound, think about fundamental theorem part 2, h prime of x is f of x. Oh, so this picture is also of h prime. Good to know. So if I'm finding h prime at 4, I am finding f at 4, and this is a picture of f. And so the value of f at 4 is this point, is indicated by that point, which is then 2. All right, the next one says to find the first point of inflection. A point of inflection is where the second derivative changes sign. The second derivative of h is the first derivative of f. So I want to look for where f prime changes sign, because that would be indicative of a point of inflection. And if you look at the picture, that's going to be right here at 3 when we go from positive slope to negative slope. So that's at x equals 3. We're changing f prime. We could give a reason here, because f changes from increasing to decreasing. Okay, which indicates that f prime is changing from positive to negative, which indicates that we have a change in h from concave up to concave down. Any of those things would be fine as long as we are labeling correctly and we say things like increasing and decreasing where we mean and positive and negative where we mean. Don't mix up those words. Okay, the next one asks to find the values of x at which h has a relative maximum on the interval. Okay, so since f is the same as h prime, we want to look for that change that we need. And the change that we need is here at 5, because we switch from being in positive land to being in negative land. Okay, so this would be at x equals 5, because h prime, which is f, is positive on the interval from 1 to 5, and h prime, or f, sorry, I forgot a 0 there, is negative on 5 to 7. And that kind of sign change indicates a maximum. The next one asks about the values at which h has its minimum on the closed interval. If I'm looking for extrema on a closed interval, I want to consider a candidate's test. There is no place, actually, where we have a change from negative to positive, so there isn't a relative minimum here. We are going to test the endpoints. So we're going to look at h of 1 versus h of 7. We already found h of 1 back in the first question, and that was 0. H of 7 means I would need the area from 1 to 7 under the given graph. And I don't really care to find that, but it's going to be a positive amount. I can kind of intuitively see that, right? All of this space in the positive versus this little bit of space in the negative sure seems like I'm going to have something that beats 0. So that would tell me, therefore, that at 1, I have my minimum. This would be more like the max. Okay, a midpoint approximation. Woo! midpoint. That's a spicy meatball there. So midpoint approximation using 3 equal intervals. I'm going to go from 1 to 3, from 3 to 5, from 5 to 7. And then I'm going to take the middle x at each one of them as my height. So that first rectangle would be 2 by 2. The next rectangle would also be 2 by 2. And then this last rectangle will be 2 by 1, but counted in the negative direction because of going down. So I've got 2 by 2, 2 by 2 again, and 2 by -1 for a total of 6. And then this last bit uses fundamental theorem part 2. I need to find g prime. I'm going to write g prime of x first. So I need to plug in my bound, take the derivative of my bound, and then technically you could be plugging in the lower bound and taking the derivative of the lower bound, but since the derivative of a constant is 0, you don't have to write this part at all if you're thinking ahead, okay? So this just tells me I want to do 2 times the function value of 2 times x for any time I want to find g prime of x. I don't know why I just rewrote that. So g prime at 3 would therefore be 2 times f of, now 2 times my input here is going to be 6. So that is going to give me -2, if you look back at the picture. Thank you so much for working through these practice problems with me, and I'll see you soon.